video, we'll explore sharp pain as part of the exteroceptive sensory system. We'll look at how sharp pain works as a warning signal for your body and how it's processed. Sharp pain is a sudden, intense, and localized sensation that acts as an important protective mechanism. It's your body's way of alerting you to potential harm or tissue damage. So now, let's set an example.
Think of a cut or a stab. This sharp pain has a rapid onset, which means you immediately know where the pain is coming from. So how do we feel this sharp pain? In our skin and tissues, we have a special sensory receptors called nociceptors. When they detect harmful stimuli, like a cut, these nociceptors transduce the signals by converting the harmful stimuli into electric signals, which are then sent to your nervous system. But what changes how we feel sharp pain? The intensity of the stimulus plays a big role. The deeper the cut, the sharper the pain. Psychological factors like stress can also increase sensitivity, while distractions, painkillers, or anesthesia can dampen the experience. Now, let's delve more into the sensor, which is nociceptors. So, how do these nociceptors work? When you experience sharp pain, it's mostly due to mechanoreceptive nociceptors connected to A delta fibers. These myelinated fibers are specialized for fast transmission of sharp, localized pain. Inside nociceptors, you'll find ion channels like piezo2 and acid-sensing ion channels, which detect mechanical stress. When activated by tissue damage or mechanical deformation, they let sodium and calcium ions flow into the cell, generating an action potential or an electrical signal that travels through your central nervous system. Now, let's follow the pathways and stations of a sharp pain signal. As we've discussed, it all begins at the nociceptors located in the peripheral tissues. From there, the signal travels through A delta fibers to the dorsal root ganglia, near the spinal cord, which acts as a relay station for the sensory input and contains the cell bodies of the sensory neurons, including nociceptors. After passing through the dorsal root ganglia, the signal moves into the dorsal horn of the spinal cord, where it is processed and relayed to second-order neurons that transmit the signal to the brain for further processing. From here, the signals immediately cross over to the opposite side of the spinal cord, the contralateral side, via the spinothalamic tract. These signals then reach the next synapse into the thalamus, which acts as a relay station, before being transmitted principally to the somatosensory cortex for perception and interpretation. As we've mentioned, the pain signals get delivered to the brain cortex. And in here, there's multiple regions that work together to process and interpret sharp pain signals. The pain signals get delivered to Brodmann areas 1, 2, and 3, located in the somatosensory cortex, in the postcentral gyrus of the parietal lobe. It's responsible for pinpointing where the pain is coming from and determining its intensity. Next, in the anterior cingulate cortex, the pain gets also delivered to Brodmann area 24 and manages the emotional response to pain, making it feel unpleasant. Now we have the insular cortex, which comprises Brodmann areas 13, 14, 15, and 16. It integrates the pain experience with bodily states, influencing how distressing the pain feels and triggering autonomic reactions like changes in heart rate and blood pressure. Finally, the prefrontal cortex, which includes Brodmann areas 9, 10, and 11, handles the cognitive aspects of pain.
So to wrap up, sharp pain is your body's fast and localized warning system. It begins with the nociceptors in your skin, travels through your A delta fibers, and is then processed by different regions in your brain, each contributing to how you experience and react to it. Understanding how sharp pain works helps us appreciate how our bodies protect us from harm, and how factors like stress or an injury can affect pain perception. Thank you for watching.